Hey all, here we are again. So let's go ahead and launch into our next lecture. So we've been talking about the structure of an atom and how what an atom is composed of and some of the various elements of that. We're now going to move to looking at how elements actually come together, how they interact with each other in the formation of various compounds and molecules. Your book gives a really nice example of just a type of molecule and something that probably is fairly meaningful to many of you if you're as busy as I am. It talks about how caffeine works. Caffeine is absolutely a molecule. It's made up of more than one type of element. It's a medium-sized molecule. The way that caffeine works is within our cells, there's a receptor for a compound called adenosine. Adenosine is a compound, and specifically in our neural cells, in our neurons, adenosine will attach to receptors within our neurons. When that happens, it makes us sleepy. What caffeine does is caffeine can also bind to those receptors. So when caffeine binds to those receptors, adenosine can't. And so when that happens, adenosine is then not able to bind to the receptor. And so that staves off some of those feelings of sleepiness. And so that's one of the ways that caffeine works to wake us up and to get us going a little bit in the mornings. So just a good example of a compound and how it works. And so, okay, so we're going to talk about two basic ways that compounds come together. And so let's go ahead and just take a quick peek. So the two basic types of chemical bonding that we're going to talk about is ionic bonding and covalent bonding. Now, at their source, ionic and covalent bonding are both all about an atom trying to have a full outer shell, trying to have a full 8 electrons in its outer valence shell. And that can happen in two different ways. One way that it can happen is with ionic bonding. Ions form, and so remember that ions form, we talked about ions last time, ions will form in order to, ions will either lose an electron or lose more than one electron or gain an electron or more than one electron. And the reason that they do so is so that they can somehow get that full valence shell. When that does happen, we then have a positively charged cation, a negatively charged anion, and opposites will attract. And so they'll stick together that way. In covalent bonding, rather than atoms gaining or losing electrons to get to their full shell, in a covalent bond, two atoms will share electrons. And so, for instance, if we have carbon coming with 4 electrons, and we'll look at this sort of notation in a little bit, what carbon might very well do is then form bonds, in this instance, maybe with hydrogen, which then comes in with some of its electrons. And then in that sharing, both carbon and hydrogen are able to fill their outer shell. And so it comes down to ionic bonding is from the formation of ions. And so the straight up giving away or receiving of electrons. And covalent bonding comes from the sharing of electrons. And so in this first video, we're going to focus in on some of the various aspects of ionic bonding. So again, as we've talked about already, atoms that have gained or lost more than one valence electron, or lost one or more, gained or lost one or more valence electrons, are called ions. Positively charged ions that have lost electrons are called cations. Negatively charged negatively charged ions that gain electrons are called anions. I haven't had enough of my caffeine yet this morning. Metals tend to lose electrons to become cations. Non-metals tend to gain electrons to become anions. And again, in both cases, they're doing that in order to gain a full valence shell. When we write the symbol for an ion, that includes the superscript with the magnitude and the sign of the charge. So for example, a calcium ion with a 2 plus charge would be written as Ca 2 plus. Now, incidentally, we do write it this way with the number and then the sign of the charge. And that's by convention, and that's also to differentiate it from oxidation number, which is something we'll be talking about later in the course. Or we might have something like nitrogen with its 3 minus charge. And again, we write the element symbol with the charge and the sign as superscripts. Metals, so like I said earlier, metals will tend to lose electrons to become cations. And they do so in very predictable ways. Our alkali metals will lose 1 electron to form here we go, form a positive 1 charge. Good God. There we go. Our alkaline earth metals will tend to lose 2 electrons to form plus 2s. And we'll skip over here, and really we only kind of talk about aluminum in this column, but aluminum will lose 3 electrons to form a plus 3. The transition metals get a little bit funny for reasons that we're not going to go into, but they can have very variable charges. And so whenever we're talking about a transition metal ion, we have to show what the charge is by using Roman numerals. And so iron with a 3 Roman numeral means that we're talking about iron with a 3 plus charge. If this were a 2 Roman numeral, that would be an iron with a 2 plus charge. Make note as well that there is a handout. Normally, if this were a live class, I would have this printed and handing out to you. But there's a good handout that goes over some of the various charges and how to find the charges. And this is also found right on the website as just a reminder of some of the resources you have. So here's our CHY 107 website. We're in the topic now, compounds and molecules, so into the materials page. And remember, there are all these informational handouts there for you as well. But I'll also try to include links in the presentations when I remember to. And so, actually, let's go back to the handout. So along with what we call monatomic ions, and so monatomic ions are these that are just like the term or the prefix mono would suggest. Monatomic ions are ions made up of only 1 atom. Polyatomic ions are now made up of more than 1 atom, so they're small compounds that also have a charge. And so, for instance, the carbonate ion is CO3, and overall the whole thing has a 2 minus charge. Or maybe the phosphate ion, PO4 with a 3 minus charge. Some of the common polyatomic ions are found on this handout as well. These are something that you do just have to memorize. You have to know these polyatomic ions because we're going to encounter them very often in this course. And you need to be able to recognize that, for instance, when you see IO3 as part of a compound, you need to recognize that that's the polyatomic ion iodate, and it has a -1 charge. You're going to have to memorize or know those, both for writing chemical equations and chemical formulas, which we'll be talking about, but also in order to name them. You're going to need to be able to when we come up with chemical names, which we'll talk about in another couple lectures, you need to know that if you see SO4, that is sulfate when it's in a compound, like Na2SO4, for instance, would be sodium sulfate, and you're going to need to be able to recognize that. And so these ions on this handout, these polyatomic ions, do need to be memorized. You need to know the names, the formulas, and the charges of all of these. I recommend color-coded flashcards. Put the name on one side, put the formula on the other, and then if you have cards themselves that are different colors, awesome. If not, use some highlighters, but use anything that you can to color code according to charge. That way you might get to a point later on when you say, oh, chlorate. I knew chlorate was a ClO3, but I don't remember what the charge was. And then you might literally visualize it in your head. You'll literally see the card in your head and say, oh, that was one of my greens. My greens are -1. So color coding like that is just another dimension to flashcard study, which can be really beneficial, and I'd highly recommend it. But whatever works for you, these do have to be memorized as part of this course. You're going to need them. And so ions then are going to come together. A metal or a cation and an anion will come together to form an ionic bond. And so that that electrostatic attraction, that plus minus attraction, are going to bring two oppositely charged ions together, and that's going to form the basis for a bond to hold those elements together. When we write the formula for an ionic compound, what we're doing is we're writing the ratio of cations to anions. And so remember that chemical formulas are formulas that show the, you can hear my kitty in the background, formulas that show the ratio of our ions. So for instance, sodium chloride means that we have one sodium in there and two chlorines. MgCl2 means that we have one magnesium and two chlorines in this compound. And so what we're going to look at is how we figure out what these formulas are, how we find what those actual subscripts are. We'll talk about the naming actually in another lecture. And here he is for a visit. Hi, kitty. Rangeley really loves talking about ionic compounds as well. And so what we always need to look for, actually, let's just move on. What we always need to look for is coming up with our lowest whole number ratio of the cations and anions coming together so that the entire compound has a neutral charge. And so, for instance, calcium, when we look on the periodic table, we see that calcium is going to form a 2+ charge. If calcium comes together with fluorine, fluorine is going to form a -1. This tells us that we're going to need 2 of those fluorines to offset 1 calcium. That's the ratio that we're going to need, 1 calcium and 2 fluorines, for the pluses and minuses to cancel each other out. And so we would end up with a formula CaF2. Let's say oxygen and aluminum are coming together. Periodic table tells us aluminum will have a +3 charge or a 3+ charge. Oxygen will form a 2-. Now it's not quite so easy, but we see that we're going to need 2 aluminums and 3 oxygens. One way to look at this is we can say, for instance, okay, we've got aluminum with a 3+ and oxygen with a 2-. Ask yourself, do my pluses balance out my minuses? Will those add up to 0? We can see that they don't. So then say, okay, what do I need more of? Do I need more pluses or do I need more minuses? In this case, I definitely need more minuses, so let's throw in another oxygen. Oxygen always comes with a 2- charge. Okay, now do they balance each other out? We can see, nope, they don't. Now I have too many minuses for my pluses. So let's throw another aluminum up there. Aluminum's going to come with its 3+. Now we have too many pluses. So we throw up another oxygen. Now finally, we're at a 6+ and a 6-. So my pluses balance out my minuses. And I have 2 aluminums and 3 oxygens for my final formula of Al2O3. Polyatomic ions, same exact principle. But what we have to do here is we have to show, for instance, in the case of calcium nitrate, so let's say we're doing this one. So Ca with its 2+, NO3 with its 1-. That's the charge on the nitrate ion. Pluses don't balance out our minuses. I need another nitrate in there. Now my pluses balance out my minuses. But what I have to do now in my formula is I have to make sure that I'm showing that it's a full 2 of these entire NO3s that I have in there. And I do that by using parentheses. This shows me that I've got 2 of the NO3 ions. If you don't have that, if you just do this, now it looks like I've got 1 calcium, 1 nitrogen, and 32 oxygens. And that is absolutely incorrect. This is our correct formula because it shows us that I have 2 of the nitrate ions. This is just another way to sort of visualize things and look at it a little bit. So if I've got magnesium and fluorine coming together, magnesium has 2 electrons here in its outer shell. Fluorine has 7. And so in order for both of these to have full outer shells, what magnesium is going to want to do as a metal is it wants to get rid of these 2 electrons. When it does that, now suddenly the outer shell will be shell 2 here, and shell 2 then is full. So if magnesium can ditch these 2, it'll have a full outer shell. Fluorine, on the other hand, if it can gain 1, then it'll have a full outer shell. So what needs to happen is that magnesium needs to give 1 electron to 1 fluorine. Now this one's full, it doesn't want to take anymore, but magnesium still has 1 left over. So it's going to give its electron to another fluorine. Now I've formed a magnesium 2+ ion because it gave away 2 electrons, and I've formed 2 fluorine 1- electron or ions. And so I get MgF2. So we've already talked about a lot of this. We can also use something that we call the crossover rule. Let's take a look at that. And so let's say, for instance, a very simple formula, Na1+, Cl1-. The charge on one becomes the subscript on the other one. But the ones we don't actually show. I just did that for illustration purposes. If it's a 1, we don't show it, just like exponents. And so we can use this crossover rule. Let's look at if maybe sodium with its 1+ comes together with oxygen 2-. Let's think about this in the way that we have already. So let's just go to a new slide for this. So in the way that we've already thought about this, we see that we need another Na. Now our pluses balance out our minuses, so we get Na2O. The other way we can think of this is simply crossing over. And so we end up with Na2O. Let's look at a much more complicated example. Chromium can form a 7+ charge. Oxygen with its 2-. So if we go through our whole entire process, okay, we need another 2-, we still don't have it, another 2-, we still don't have it, another 2-, we still, now we're at 8. Now we need, so another 7+. Now that brings us to 14. So we need another 6 here. 2, 3, 4, 5, 6. Oh, sorry. I don't know where my head is with my math. We don't need another 6. Told you, not enough coffee yet this morning. But now we've done it. So now we've got 14 pluses, and we have 1, 2, 3, 4, 5, 6, 7, 14 minuses. So we get Cr2O7. Let's look at our crossover rule. Cr with its 7+, O with its 2-. We get the crossover, and we get Cr2O7. So this crossover rule will work. And I forgot that I did have some slides here on it. So same thing, Na2 and or Na1+ and S. So we can see that the charge on one becomes the subscript on the other. But then we omit the 1. We get Na2S. The crossover rule will work, but you have to be aware of one thing. Remember, we're always looking for the lowest whole number ratio. So let's say you have barium 2+ and oxygen 2-. You would do your crossover rule, and you'd get Ba2O2. That's okay if you understand that that's an intermediate step. With an ionic compound, you would then always simplify it down to the lowest whole number ratio. With an ionic compound, we'll talk about covalent compounds in a little bit. You would not necessarily reduce down with a covalent compound. But with an ionic compound, you would always reduce it down to its lowest whole number ratio. The same way that you would never leave an answer as 4/8, you would always reduce it down to 1/2. A high school math teacher that I used to work with, Miss Hodgson, if you left an answer as 4/8, she would probably slap you across your face. She really wouldn't. She was actually a very nice lady, but she had a reputation for being mean. She really wasn't. She was a nice lady and a great math teacher. But anyway, you would never leave an answer as 4/8 in her class, or you would be made aware of it. Same thing here. Don't leave an answer that you can reduce down for an ionic compound. Always bring it down to what you can reduce it to. And we've already talked about polyatomic ions. And so now practice a few. So go ahead and see what you can come up with for these. Pause the video each time. See what you can come up with for the formula for sodium and bromine. So you've got NaBr. Now try for sodium and oxygen. Pause the video each time and try these. We get Na2O, aluminum and chlorine, AlCl3, barium and chlorine, BaCl2, aluminum and oxygen, Al2O3, and finally magnesium and oxygen, MgO. Now a few with polyatomic ions. Try aluminum and sulfate. Feel free to look up the polyatomics for now, because I'm sure you don't have it memorized yet. But aluminum sulfate, we get Al2SO4 magnesium and hydroxide. We get MgOH2, potassium and acetate, KCH3CO2, and finally calcium and nitrate. And there it is, CaNO3 too. And that is all for our ionic compounds. In the next video, we're going to start looking in a little more detail at covalent compounds. And so with that, you stay classy, USM.